Share your screen. You can do it. You can do it. There you go. I'm so proud of you, iPad. All right, so your final exam. So it will be posted this Friday or by Friday. Okay, and you will have until the end of the regularly scheduled final exam time to turn it in. And I'll have to look up what that is, and I'll let you guys know probably on Friday when exactly that is. So the only constraints are you work alone. Okay, so whereas with your homework, that's a home, no. Whereas with your homework, I don't care. In fact, I encourage you to all work together. For your final exam, I insist that you work by yourselves. Okay, so you're all on your honor to do it all by yourselves. Okay. The second thing is that you start working on it and something isn't clear. So you want to ask some questions in order to clarify something about the exam that you don't understand. So now I want to keep this fair for everybody. So the way this is going to work is that you will email me your question, okay? And I will get it. And then I will respond with the answer. But when I will respond not just to you, but I will respond to everybody, okay? So whatever question anybody asks, I'm not going to specify who it was that asked it. So you don't have to be worried about, oh my God, I'm worried I'm going to look dumb or what. Don't worry about that. But I will reply to everybody in the class, giving both the question that was asked and the answer to it. So everybody will get to see the same information. Okay, so email questions, and I will respond to everybody, all. Okay, so everybody will see the same thing. Okay, and I think that's about it. If anybody has any questions about how this is going to work? So typically this is how final exams in graduate school go, except you're not given quite as much time, but typically the format is the same. So, if you intend to go to graduate school, then here I'm getting you ready for it. All right, so is everybody cool? All right, very good. So then let us talk about physics again. Okay, so now we were starting on Monday to talk about quantum mechanics applied to statistical mechanics. Okay, but before we get too into the quantum mechanics, I want to first of all emphasize this other exciting development that we had encountered called the partition function. All right, so way back towards the very first week of class, we showed that in general, the probability density distribution of finding some energy of your system, finding the energy of your system equal to some specific value was proportional to this exponential of e to the minus beta times that specific value of the energy, where beta is the inverse, what's called the inverse temperature. It's 1 over Boltzmann's constant times the temperature. Okay. Now, so what we showed on Monday was that in order to make this an equal sign, that what you have to do is to make sure that this probability density is normalized. All right, so in order to make this an equal sign, what you have to do is to normalize it. What the? Okay, and so to normalize it, all you have to do is to take each of these individual Boltzmann weights and just add them up for every possible state that you can have. All right, so the normalization factor is simply the sum over all possible values of E star of this, what's called the Boltzmann weight, e to the minus beta E star. Okay, so now this thing, which we introduced as a normalization constant, is in fact far more useful than that. This is the partition function, which you call z. Okay, so the partition function z is simply this, this exponent e to the minus beta ei summed over all possible values of I. And this is for discrete values of the energy. If you have continuous spectrum, you would integrate instead of doing a discrete sum, but it's, you know, it's exactly the same idea. All right, so now the one thing I wanted to emphasize was that this is correct when you're talking about the canonical and microcanonical ensembles. Canonical and microcanonical. Okay, so this is how you write down probability density distributions in terms of the partition function in the canonical and microcanonical ensembles. Okay? All right, so now the next thing we started talking about was quantum statistics. Okay, and as an example of a quantum mechanical system, the example we gave on Monday was a quantum mechanical harmonic oscillator. So a quantum mechanical harmonic oscillator. Okay, so a quantum mechanical harmonic oscillator that by definition has some quadratic potential, like so. Okay, and what you do, so your potential looks like this. So this is the energy, this is the position, and your potential function is just a parabola, right? So you take your particles, you throw them into this parabola potential, and you see how they bounce around in there. Okay, so now when you solve this problem with quantum mechanics, what you do is you take this potential function and then you stick it into the Schrodinger equation. Okay, so now let's see if I can remember what the Schrodinger equation is. I believe it's minus h bar squared over 2m Laplacian of psi plus u psi is equal to minus, oh, let's not get that fancy, the energy times psi. All right, so in order to make this problem quantum mechanical, you simply take this quadratic function and you plug it in here to the Schrodinger equation, and then you solve the Schrodinger equation to tell you, so now then you take this equation and you solve to get what the psi's are. And what you get is that the psi's can be some specific set of functions. What are they called? I don't remember what those functions are called. Is that the Hermite polynomials for the quadratic, for the harmonic oscillator? I don't remember. It doesn't matter. Okay, so you get some specific set of wave functions that will satisfy the quantum harmonic potential. And each of these wave functions corresponds to some discrete value of the energy. All right, and in particular, the value of the energy that you get is equal to 1/2 plus n h bar omega, where n can be just some integer. Okay, so now what that means is that what you've got is a set of energy levels, like so. Okay, so this would be your ground state, E0. This is your first excited state, E1. This is E2, E3, so on and so forth. So this one would have energy h bar over 2 omega. This would be 3 h bar over 2 omega, so on and so forth. All right, so now this was the Schrodinger equation. When you do this in the context of quantum mechanics, what you're doing is you're just throwing in one particle and you want to see what the wave functions of that one particle behave like. Now, what we're going to do in statistical mechanics is instead of just one particle, what we're going to do is throw in a whole crap load of particles. Okay, so we're going to throw in just a large collection of particles. And each one of these particles is going to settle into one of these energy states. And in general, what we want to do is to calculate, on average, what are going to be the occupation numbers of these energy states. Okay, so in general, the problem that we want to solve is to calculate these average occupation numbers. Okay, then once you have the average occupation numbers, it's trivial to get the energies, right? Because the energies are given for each particle. There, you know what the energies are simply by what energy state they're in. So you just take the number of particles that you find in that energy state, multiply it by the energy of that state, add them all up, then you've got the total energy of your system. So once you have these occupation numbers, it's very easy to get the average energies of your system as well. Okay, so that's what we're going to do, is we're going to take these quantum mechanical systems, we're going to throw in particles, we're going to apply the magic of statistical mechanics in order to try to determine our average occupations and average energy states of our systems. Piece of cake. All right, but now there is a complication. Okay, we've already talked about this a little bit when we talked about black holes. All right, so the complication is that intrinsically in quantum mechanics, the number of particles that you are talking about in your system is typically not a constant. Okay, so in quantum mechanics, in the number of particles is generally not a constant. Okay, now, why is that? It's very easy to understand. That is the case simply because of this. E equals mc squared. Okay, if you have a given amount of energy in your system, quantum mechanics says that you can take that energy and convert it into mass. That is, you can convert it into particles. All right, so as long as you have enough energy, you can generate more particles. And similarly, if you have the right kind of particles, like you have a particle and its antiparticle, they can annihilate one another just to produce pure energy. So in quantum mechanics, just intrinsically, you are able to more or less freely increase or decrease the number of particles in your system. All right, so N is not fixed in quantum mechanics, generally speaking. All right, so now what that means is that this business that we talked about up here, the quantum and the canonical and microcanonical ensembles, where we talked about this, you can't do this, because in the canonical and microcanonical ensembles, by definition, the number of particles is fixed. All right, so now what that means is that when you do quantum statistics, you more or less naturally have to work within the grand canonical ensemble. Okay, so the fact that N is not generally fixed in quantum mechanics means that you're going to need to work in the grand canonical ensemble. All right, so so we've talked about this a little bit previously, but now let's just refresh our memories about the grand canonical ensemble. All right, so the idea behind the grand canonical ensemble is that you have a microcanonical box, that is where the energy, total energy inside your box is fixed. Okay, so here's my box. The walls of the box are made out of unobtainium, and hence no energy gets in or out, no particles get in or out, so on and so forth. Okay, now the way that we're going to formulate this in terms of quantum mechanics is we're going to say that this box is huge, okay? So the box is going to be what I'm going to refer to as a bath. So it's in general very big. And our system is going to be just some small component inside the bath. All right, so in general, the size of the system that we are interested in is minuscule compared to the size of the bath. All right, so in other words, a V system is much, much less than V bath. Okay, now the way that we're going to define our system is, again, it's grand canonical. And what that means is that we can exchange energy in the form of heat or whatever. So we can have energy being exchanged between our bath and the system that we're interested in. And we're also going to allow particles to be exchanged. Okay, so this is a natural way to allow the number of particles within your system that you're interested in to not be fixed, is that you can just think of it as exchanging, gaining or losing particles from the bath that it is immersed in. Okay, now for most of the systems that we're going to be interested in, we're not going to worry about volume. Okay, so when we first introduced the grand canonical ensemble, we said you can also allow the volume to fluctuate. We're not gonna worry about that at this time. Okay. All right. So in other words, the total number of particles in our system is still going to be conserved. So this is a constant quantity that is equal to the number of particles in the bath plus the number of particles in our system. Okay. So in other words, the number of particles, so this is going to become relevant shortly. You can express the number of particles in the bath as equal to the total number of particles in your system, not your system, your box, minus the number in your system. Okay, similarly with the energy of your bath is equal to the total constant fixed energy of your box minus however much energy is in your system. All right, everybody cool? All right, so now what we want to do is to essentially determine what we showed in the microcanonical and canonical ensembles was that the probability density of having some energy E was proportional to E to the minus beta E, right? So now what we want to do is to derive the corresponding expression for the weight in the grand canonical ensemble. All right, and we're going to do this a little bit different than we did it before for both the canonical and microcanonical systems. But if you apply, and just in case you didn't follow or you didn't like the way we derived it previously, what I'm going to show you is another way to get it that would apply equally well to the microcanonical and canonical ensembles. And so, you know, if you like this one, you can go back and think of deriving this exponential factor for the canonical ensemble in terms of doing it this way too. Okay? All right, so we're going to start out the same way we did previously when we were talking about equilibrium states. Okay, so again, what we want to calculate is our probability density. All right. Now, specifically, we want to calculate the probability density of the energy of our system. So let me call that ES. I should do it in blue just to be super specific about what I'm doing. So in general, what we're interested in is the behavior of this system. All right, the system that's immersed in the bath. So what we want to calculate is the probability of finding the energy of that system equal to some specific value. Okay, and the number of particles in our system equal to some specific value. Okay. Now, going way, way back to when we first started, what we're going to say is, again, because our entire system composed of our a little system immersed in the bath is microcanonical, then this probability density is going to be proportional to the volume occupied by those states with the totals with a correct amount of energy and number of particles in phase space. All right, so in other words, this is going to be proportional to our density of states, okay, for our system to have these specific values. All right, so again, this is the kind of thing we've done previously. Now, because of these relationships, again, the total number of particles and the total energy in our box is fixed. If we specify the specific value of the energy and number of particles of our system, we must also specify a corresponding value of the energy and number of particles in our bath. All right. So in other words, this omega for our system is also going to be proportional to some omega for our bath. Okay, and that's going to depend upon the energy values of the bath and the number of particles in the bath. Okay. All right, so another way to write this is that the probability density that we are interested in is proportional to the density of states of the bath that is a function of the energy of the bath, which you can write from here in terms of the total energy of the box minus the energy of your system. And similarly, you can write the number of particles in the bath from this as the total fixed number of particles in the box minus the number of particles in your system. All right, cool? Cool. Okay, so now this is we've done this before. We've done exactly this before. All right, so now the one of the new tricks we're going to apply is that now what we're going to do is we're going to relate this to the entropy. All right, so we have that the probability density is related to the density of states. But we know that the density of states is also what determines the entropy. Okay, and we know that the density of states is related to the entropy by kb log omega, right? So in other words, what this tells you is that omega is equal to the exponent of S over kb, right? Okay, so in other words, rho is going to be proportional to the exponent of the entropy. Instead of writing it in terms of the density of states of our bath, I'm going to write it in terms of the entropy of our bath. Okay, and again, this entropy is going to be a function of the total energy of the box minus the entropy of the system, and the number of particles in the box minus the number of particles in the system. Oh, and I forgot Boltzmann's constant, excuse me, divided by Boltzmann's constant. All right, so pretty straightforward so far, I think. Has anybody got any questions? Are we good? All right. I'll take that as a no. Okay, so now what we're going to do is we're going to apply a trick. Newton's fourth law, my friends. We're going to go back here to this. Okay, so we're going to appeal to the fact that the volume and therefore the energy and the number of particles of the bath is much, much greater than the number of particles and the volume and the energy of our system. Okay, so in other words, what we have here is the entropy of our bath expressed in terms of a constant minus a very small number. Okay, because again, because the size of our system relative to the bath is so small, that means that the total amount of energy that's inside that box is going to be very small, proportional to the total amount of energy in the whole box. And same argument for the number of particles. Okay, and so again, this is a constant, and this is a small number. All right, so now you have a function of a small number. What are you going to do? Newton's fourth law, you're going to Taylor expand, right? So we are going to expand the entropy around E, the total fixed energy of the box. All right, so what you get, so again, this is just pure math. All right. So the entropy of the bath, which is, again, the energy of the box minus the energy of your system, and a function of the number of particles in the box minus the number of particles in your system, If you Taylor expand this, you can say that this is approximately equal to just the entropy of the bath evaluated when it has all of the energy in the box minus the energy in your system times the partial derivative of the entropy of the bath with respect to the energy evaluated at the, let's do it like this. Okay. And then because we have two variables, we've got both the energy and the number of particles, then you also have this other term. So this is, again, the number of particles in your system times the partial derivative of the entropy of the bath with respect to the number of particles evaluated at n prime equals n. So that's just pure Taylor expansion. And then, of course, plus higher order terms. Higher order terms. Which, again, because we're assuming that E system and N system are small, we are going to neglect these higher order terms. All right, so let's take this expansion and plug it into our probability density. All right, so what we get is that rho is equal, well, approximately equal to the exponent of the entropy of the bath when it has all of the energy and all of the particles. Oh, sorry, I forgot that here. This should also be E n, there we go, divided by Boltzmann's constant, right? Minus the energy of your system, again, divided by Boltzmann's constant, times the partial derivative of the entropy of the bath with respect to the energy. And we all understand that those are supposed to be evaluated at some specific value, so I'm not going to write it in order to keep it clean. Minus the number of particles of your system divided by Boltzmann's constant times the partial of the entropy of the bath with respect to the number of particles. All right. Okay, now we go back to our old friend thermodynamics. So from thermodynamics, we remember, okay, specifically, we remember that the partial of the entropy with respect to the energy, that's 1 over the temperature. The partial of the entropy with respect to the number of particles, that is equal to the negative chemical potential divided by the temperature. Okay, so we take this and we plug it in there. And we take this and we plug it in here. And what we get is that rho is proportional to the exponent of the entropy of the bath divided by Boltzmann's constant minus the energy of the system divided by kBT. Ooh, that looks familiar. And then the fact that we're allowing the number of particles to vary gives us this other term, that is mu n system over kBT. All right, so everybody's cool? All right, excellent. So now this is what we've got. We've got that our probability density should be proportional to this exponent of these series of terms. Now, keep in mind, remember, this is for the grand canonical ensemble. For the canonical ensemble, the number of particles is fixed, okay? And if you go back through this same derivation, keeping the number of particles fixed, what's going to happen is that this term is not going to be there. All right, so what you're going to have is just the entropy of the bath minus the energy of the system over kBT. All right, that looks very familiar, right? Okay, so now to make it look even more familiar, now what we want to do is to make this into an equal sign. How do we make that into an equal sign? Again, the way we make it into an equal sign is that we have to make sure that everything is normalized. All right, so in order to make it normalized, what we have to do is divide by the same exponential summed over all possible values of the energy and number of particles in your system. Okay, so in order to make this a equal sign, we will do this. It is equal to the exponent of the entropy of the bath minus the energy of the system over kBT plus mu in system over kBT. And then we just divide by the sum over all possible values of E system and N system of this same thing. All right. Now, note it, this first term, this thing, here and here. This only depends upon the fixed total energy inside our box and the fixed total number of particles inside our box. So in other words, when you perform this sum, that doesn't affect this first thing at all. All right. So in other words, what you can do is take this first factor that only depends upon the entropy of the bath as a function of the total energy and number of particles of the box and just factor it out of the sum. Hell, let me just do it. All right. So that I don't have to imagine that you understand what I'm talking. I'm just going to do it. So what you get is that E to the S bath over KB factors out of, and now I'm going to replace 1 over KBT with beta. Okay, so you get that. And again, because this does not depend upon the energy or number of particles in the system, you just factor that out of the sum too. And again, the sum is over all values of the energy of your system and the number of particles in your system. And now you can see you got the same factor that depends upon the entropy of the bath in front of, so it just cancels out. So in other words, you just don't have to worry about it. Okay, so in other words, so let's summarize, within the grand canonical ensemble, the Boltzmann weight is proportional to the exponent of minus beta E. So this is what you would get if it was the canonical ensemble. And then because you're also allowing the number of particles to vary, you also get this other term that depends upon the chemical potential and the number of particles. So that is the Boltzmann weight in the grand canonical ensemble. Very important. Okay, now again, to normalize this thing, you divide by the sum over all those things. And that yields what is referred to as the grand partition function. Okay, so it's exactly the same idea as the partition function in the canonical ensemble. It's just that you've got this extra. So you're going to sum over all values of E and N of the exponent of minus beta E plus beta mu N. Okay, So this is the grand partition function. So it's the same as the partition function for the canonical ensemble. You just have this extra factor that depends upon the number of particles. Okay, now, just for your own self-edification, again, what you have is an exponent of a sum of two terms. You can also write this trivially like this, e to the minus beta e times e to the minus beta, no, plus, excuse me, e to the beta mu n. All right, so this is your typical canonical Boltzmann weight. So in other words, without this term here, it's just your typical partition function. And then when in the grand canonical ensemble, you multiply by this additional exponent that depends upon the number of particles. So this thing has its own name, which you may hear sometimes. It's given the symbol little z and is referred to as the fugacity. All right, so the fugacity is simply the exponential of beta times the chemical potential times the number of particles. Okay, where am I? All right, so now what does this do? So now, okay, so let me show you what you can now do with this. Okay, so what can you do with this? So in other words, what I'm going to show you now is how do you extract information from the partition function, or in particular, in this specific instance, from the grand partition function. All right, so now what we're going to do is define another function. Okay, and I'm going to call this function capital phi. And this is simply equal to, I'm defining it now, equal to minus Boltzmann's constant times the temperature times the logarithm of the partition function. And you're going to say, why are you doing this? And again, it's because I've eaten enough of the spice that is Cheeto dust that I know what's going to come. So as you'll see, there's a very good reason for defining this function. All right, so this is what's referred to as the grand free energy. Okay, if this, and that's because this is the grand partition function. If we were working in the canonical ensemble and this were just the regular partition function, this would be what you would just call the free energy. But because we're in the grand canonical ensemble, it's the grand free energy. All right, so now what the hell is it? So first of all, this is not terribly important. I just want to show you this. So you can show that this thing is a function of the temperature, the volume, and the chemical potential. And this thing will also, if you go through thermodynamics deep enough, this thing will also show up in thermodynamics. And in thermodynamics, you can show that this is equal to the energy of your system minus the temperature times the entropy minus the chemical potential times the number of particles. Okay, and keep in mind the energy here is a function of the entropy, the volume, and the number of particles. And so what all this is, again, maybe you've seen this before in thermodynamics. This is simply a Legendre transformation. Okay, which all that means is it's simply it's an energy, right? It's related to the energy, and all you're doing is changing variables, right? So the natural variables of the energy are the entropy, the volume, and the number of particles. And by subtracting off these two terms, you can see that what that does is it changes the variables of the grand free energy to being the temperature instead of the entropy, and the chemical potential instead of the number of particles. So again, if you didn't follow that, no big deal. I just wanted to emphasize that this thing is essentially just an energy expressed in different variables. All right, so now we have this thing. And now it turns out that once you have this thing, once you have the grand partition function, and therefore, okay, once you have the grand partition function, and therefore you also have the grand free energy, you know everything. All right, so let me show you. Okay. So, for example, so now again, we're talking quantum mechanical system. We're going to allow the number of particles in our quantum mechanical system to fluctuate freely because it's in contact with some bath. So then you ask yourself, on average, how many total particles are going to be in our system? Okay, so for example, let's calculate the average total number of particles in our system. Okay. All right, and again, just to remind you, all this is because we have a quantum mechanical system, we have discrete energy levels. Each one of these energy levels is going to have some number of particles in it. All right, so this is, for example, N0, N1, N2, N3, etc. Okay, and so to get the total number or the average, what you want to do is essentially to add all these things up. Okay, so in particular, before we calculate the total number of particles, let's calculate the average number of particles in, no, let's not do that. So, okay, here we go. So average number of particles. How do you do this? Well, you just go back to the very first day of class, right? So what we're doing here is we're calculating the expectation value of N. All right, so we know from the very first day of class that what you do is you take that thing, and again, this is going to, we have discrete energy levels, so we have some, we have to specify the energy levels that we're talking about, times the probability density to find that number of particles, and then you sum over all values of M. So this is just the definition of how you calculate an expectation value. Okay? All right, so now how do we do this? So now we know what rho is now. So let's write it out. So it is this. Okay, so our N, and then rho is simply our Boltzmann weight that we just figured out for the grand canonical ensemble. So it's E to the minus EM minus mu NM over KBT divided, and then we have to divide by the partition function. So the partition function is, again, the sum over M E to the minus EM minus mu NM over KBT. All right, so there it is. Okay, now what? So now notice the numerator and the denominator look very similar to one another, right? So the numerator has this exponent in it. The denominator has that exponent in it. And both the numerator and denominator, you're summing over all possible values of M. The only difference is in the numerator, you have this extra factor of the number of particles. Okay, so now I ask you to notice a cute mathematical trick. So notice that in M, E to the mu nm over kBt. Okay, so notice, so this nm, that's here. So that's right here. This is the same thing as kBt if you take the derivative with respect to mu of e to the mu in m over kBt. Right, so if I have this exponent and I take the derivative of it with respect to mu, what that's going to do is to pull down a factor of nm over kBt. So again, let me just do it. So this is kBt times, when I take the derivative of this exponent, I get nm over kBt times e to the mu nm over kBt. So the kBt's cancel, and I'm left with this thing. Okay. So this, whoops, that's a silly looking sigma. So if I sum over all m, n sub m, e to the mu nm over kBt, this is the same thing as kBt sum over all m times the derivative with respect to mu of e to the mu nm over kBt, right? This derivative is with respect to mu, which does not mess with the m's in the sum. So in other words, I can pull that derivative through the sum. And so this is d mu of kBt times the sum over m of e to the mu nm over kBt. That thing is just z, right? That's my partition function. So this is d mu of kBt times z. Okay. Now notice that this looks now very, very similar to the numerator of this thing, right? But now we also have this extra factor of z in the denominator. Okay. So now notice that if I were to take the logarithm of z instead, so if instead I did this, dd mu of log z, that would give me 1 over z dz d mu. Okay. So now let's put everything together. We have that the average number of particles, which again, essentially by definition is equal to this, n sub m e to the minus em minus mu nm over kBt divided by e to the minus em minus mu nm over kBt. I can write this as 1 over z d mu of kBt z. This is the same thing as d mu of kBt log z. In other words, minus d phi d mu. All right, so in other words, in general, once you have your partition function and therefore your free energy, The way that you extract information out of it is that you just take that free energy and you take appropriate derivatives of it. Okay, so here, for example, you can see that we were interested in the number of particles. All right, so what you do is you look at your Boltzmann weight and you see, oh, the thing that I am interested in here in the exponent, that is multiplied by mu. All right, so then what I do is I take my free energy and I differentiate with respect to mu. And when I do that, that pulls down this extra factor of n sub m and therefore gives me the average number of particles. All right, similarly, if you were interested in the average energy, all right, the average energy is, it's a little bit more complicated than this, but the average energy here you can see is multiplied by 1 over kBT. So if you want the average energy, then you could just differentiate with respect to 1 over the temperature, for example. All right, and that would pull down a factor of the energy. Then you have the average energy. Okay, so in general, what you want to do is you figure out what your partition function is. Once you have your partition function, you can then just take the logarithm of it, which gives you the free energy. And then you just take appropriate derivatives of the free energy in order to calculate your expectation values of whatever it is that you care about. All right, does that make sense? All right, and so we're out of time. When we come back on Friday, we're just going to essentially do a whole lot of this. We're going to start writing down specific systems. From those systems, we calculate what is the partition function of the system, and then once you know the partition function, you just start taking derivatives, and that tells you everything about that system. All right, so again, we're out of time, so I'm going to call it quits there. We're actually more than out of time, but that's it. So does anybody have any questions? All right, very good. So then on Friday, we're just going to do a whole lot more of this, all right?
Wait, I have a question.
Yes, please.
At the start of the class, sorry, my neighbors are really being really loud. Why is n generally not constant again? Could you repeat that?
So n is generally not constant because of pair production and annihilation of particles. So in quantum mechanics, if you have energy, you can produce particles from that energy because E equals mc squared. All right, so for example, a photon, which has a given energy, can just spontaneously turn into 2 massive particles just by converting that energy into mass. All right, and because you have this free interconversion between energy and mass, then the number of particles in general is not going to be fixed.
Oh, so like so photon going into 2 electrons, like something like that, right?
Well, it'd be a photon going into an electron and a positron.
Oh, yeah,
yes.
electron positron.
Yeah, but
okay.
Exactly that kind of thing. Yes, exactly.
Okay, thank you.
Yep. All right, so I'll see you guys on Friday. Stop share, end meeting.